In this video, I'm going to briefly go over solution concentrations and converting between one type of concentration unit to another concentration unit. Most of this stuff you should probably be familiar with already, but we'll just quickly go over them anyway just to make sure we're all on the same page. So molarity is the concentration unit that you have used over and over and over again, and you're probably the most familiar with. So just recall that molarity is the moles of solute per liter of solution. You may also see it as millimole per milliliter. And to do molarity calculations, you will sometimes need to figure out the moles of a particular solute when given the number of grams of that particular solute that was added to a solution. Okay, so you will need either grams per mole or milligrams per millimole when doing that type of calculation. Percent composition, you may or may not be familiar with this. Okay, so we have a weight percent. That could also be shown as percent weight over weight, and that is just going to be the mass of the solute divided by the total mass of the solution or mixture times 100%. And a volume percent is a similar calculation, just using the volume of the solute and the total volume of solution, and that can be expressed as percent volume over volume. Parts per million and parts per billion are concentration units that come up a lot more when we're talking about environmental samples or samples that have very low concentrations of components that we're interested in. So there are two definitions of part per million and part per billion that you should become familiar with. The first is the exact definition, and that's when we're only dealing with masses of substances and masses of samples. So part per million, or ppm, is the mass of a substance divided by the mass of the sample times 10 to the power of 6, or times a million. For part per billion, or ppb, the calculation is nearly the same as for part per million. It's still the mass of a substance over the mass of the sample, but in this case we're multiplying it by 10 to the power of 9, or 1 billion. Now you run into that definition of part per million every once in a while, but it's more common to run into the approximate definition of part per million and part per billion. Okay, so especially in lab, you will be using those particular concentration units. So know that 1 part per million is the same as a milligram per liter, and a part per billion is the same as a microgram per liter. So one thing you'll need to become familiar with is how to convert one concentration unit to another. Now, this particular example here is fairly simple, and I hope you could all do this. So converting 1.25 molar sodium hydroxide to grams of sodium hydroxide per 100 milliliters, and given the molar mass of sodium hydroxide as 40 grams per mole. So to do this, we can start off with our starting concentration. So we have 1.25 molar, which is the same as mole per liter. And then we're trying to convert this into grams per milliliter. So first thing we can do is we can use the molar mass of sodium hydroxide and convert the moles into grams. Okay, so our moles have now canceled out. So now we have grams per liter, but we need to have grams per 10 milliliters. So we can now convert the liters into milliliters. So if we times 1 liter is 1,000 milliliters. So now the liters cancel. So at this point, if we do the calculation, we will have grams of sodium hydroxide per 1 milliliter of solution. So then if we just multiply this by 10, that's going to give us per 10 milliliters, and then the answer that we're going to get out of this is 0.500 grams. Okay, so you should be familiar with how to do these types of calculations. The rest of the calculations we do here are all going to be unit conversions, and that is a lot of what the concentration units conversions are in chemistry. Taking one concentration unit, converting to another, it's just a unit conversion. Okay, so as I said, most of the calculations you do are unit conversions, and as I did in the last example, it's a good idea to write out all of the conversion factors, because then you know that the units cancel correctly. I've seen so many times where students will try to shortcut a calculation and end up inversing one of the conversion factors. And then what happens with that is if you look at what units would actually come out of that, they end up being really weird, something like grams squared per liter, which doesn't make any sense. So make sure that the units cancel properly. So here's just a silly example for unit conversions, and I'm not going to do it for you, but I will give you the answer. The answer ends up being 602 liters of Mountain Dew. Okay, so let's just go over a couple examples. So this one is on molarity. The question is, what is the molarity of sodium chloride in seawater if 2.7 grams of sodium chloride are dissolved in 1 liter of water? Okay, so we're trying to figure out a concentration here, and we are given the molarity of, we're given the mass of sodium chloride, and we're giving the volume of the water that it's going to be dissolved in. Okay, so usually in these calculations, if you're given a mass, and especially if you're trying to find molarity, you should know that you need to convert grams into moles. So the first calculation here, figure out the moles of sodium chloride. So we have grams of sodium chloride on the top, and then the molar mass there. You could also write it as 2.70 grams of NaCl times 58.44 grams of NaCl per 1 mole. Okay, and then in this case you can see that the grams of sodium chloride cancel, and we still end up with 0.046 moles, but that could also be written as 46 millimoles. Now we have moles. We're given the liters of solution, or the liters of water that we're going to be dissolving that in. So then we just take our moles divided by liters, and that gives us our molarity. We can write it as 0.460 molar or 460 millimolar. Either way is acceptable. Okay, here's one converting part per million concentration to molarity. So a polluted lake found to have 148 part per million of nickel. Convert this to molarity, and we're given the molar mass of nickel. Okay, and recall that 148 part per million is equivalent to 148 milligrams per liter. If you don't recall that or don't remember that, then it's really going to be difficult to do any kind of unit conversion, because part per million itself, if you're just looking at that, there's nothing that you can cancel with it. But if you have milligrams per liter, you should be good. So we start off with our 148 milligrams per liter, and we're going to convert milligrams into grams using this. Right, so now our milligrams have canceled. We're left with grams per liter at this point. But we're asked for molarity, so we know that we should convert grams into moles. So this is the molar mass of nickel, so that we have 1 mole of nickel per 58.69 grams. The grams now cancel, and we're left with moles per liter. And that ends up being our answer, 2.52 times 10 to the minus 3 molar. So the one last thing that I want to go over very briefly is stoichiometric calculations. And there's one lab that you'll be doing called determination of macro concentrations of iron by oxidation with dichromate, where this type of calculation comes in handy. So if you want some practice with this, or a sample calculation, you can look at page 51 of your lab manual and you will see that. But another example is on page 24 of your textbook, example 2.6. So you're given this particular equation here, and you have to realize that in this chemical equation, 2 moles of iron are reacting with 1 mole of oxalic acid. So when calculations are being done with respect to this chemical equation, you have to realize that when you are finding, for example, the moles, how many moles of oxalic acid are needed, or how many grams of oxalic acid might be needed to react with iron, then you have to make sure to take the stoichiometry into account. Okay, so it's not a 1-to-1 stoichiometry, it's a 2-to-1. So depending on how you do the calculation, you either have to multiply a number by 2 or divide a number by 2. So again, if you need an example, check out page 51 of your lab manual. This is something that you have done before, so you should be familiar with this. Check out your textbook a little bit more if you need some more information on that. So this is about all I have for this particular section. In the next section, we'll talk about preparing solutions, which is going to be another skill that is important and that you will do a lot of in the lab.